Everywhere we go today, we are surrounded by things using what's called artificial intelligence. Cameras and video recorders use it to make decisions for us, how to focus, engage exposure, or record the right program from the television set. New generations of sophisticated electronic machines can diagnose their own problems and prescribe remedies. All over the world, scientists are at work on projects which mimic aspects of human intelligence, giving machines a limited capability to make their own decisions. Here, scientists are developing a surveillance machine that reproduces the human ability to track motion. No one claims that any of this work will actually replicate human intelligence in its entirety. At the moment, everyone agrees that so-called artificial intelligence is only partial intelligence. But some scientists, proponents of what is known as strong artificial intelligence, believe this process will, one day, go much further and replicate human intelligence fully. This is a materialist view, where the brain and everything in it, consciousness, soul and all, is just physical material.
I think within perhaps 50 years, machines as intelligent as human beings, but different in many detail, will exist. Sometime after that, possibly after several generations of scientists of the robotic variety work on the problem, it may become possible to scan a human brain in sufficient detail and with sufficient understanding to replicate its function in other hardware. So it may be possible essentially to read out a human personality and install it in some kind of future supercomputer. And then you would in fact have transplanted the soul of a person into a machine. What especially excites me about this line of development is that it offers a way to break most of the bounds built into our bodies and our biological minds. By transferring our mental skills into machinery and re-engineering them in a way that makes sense, we can do things like increase memory, increase computing speed, increase the skill repertoire. We can also build bodies which can live in many places that biological bodies certainly could not. And it would allow us to do things, us in this expanded sense, that now we can't even imagine. It's a process of exploration of territory that's very interesting. The concept of building robotic progeny, which will exceed us and essentially take over our functions and go where we could possibly not have gone before, is really unprecedented in human history. There's nothing in our past that's really quite like it. So there is really no natural way to feel about it. The best we can do is to map it into things that are similar to things in our past. And there are several distinct categories of things we can map it into, and some of them are bad and some of them are good. For instance, we can imagine that these artificial minds are really some kind of foreigner. They're the people of the next tribe coming down to take over our territory and throw us out. And then we feel very defensive about it, and we would want to stop them at all costs. On the other hand, the idea that we're building things bit by bit, instilling in them our values, our skills, they're gradually becoming more competent. That's very much like the way we treat our children. So thinking of these things as our children makes them entirely a positive thing. It's natural that they should take over from us in the future. And in fact, our continued survival is through them.
I'm a scientist, and I too believe in the power of the human mind to make progress. But as a scientist, I also believe in certain inbuilt limitations on what can be scientifically achieved. And this is what I shall argue in this program. The human mind may have invented the computer. It has not invented a computer that can invent a human mind, nor will it ever be able to do so. The prospect of thinking machines has always fascinated us. They've long been a staple of popular culture, in films ranging from Fritz Lang's futurist masterpiece Metropolis to the androids in modern action movies like Blade Runner and Terminator. Here, human minds are like human bodies, just physical artifacts which can be and are replicated in computers. But the robot woman is still missing something. And most people seem to think this will always be missing.
If you've got the machine programmed by an individual, the most you can hope to do is replace some of the emotions of that individual. But you're never going to have that total individuality, you know, the emotional side of it. I mean, it would be impossible, wouldn't it?
Yeah, I think we've got a certain ingredient you just can't put into a machine, really.
Surely must be a secret ingredient, which is soul. Soul exists, yeah. And it don't exist in a microchip, so yeah, we're pretty definite about that.
It's a function within a human being, which has been gifted to us, so, yeah.
What's inside, I don't know, human personality, you can never replicate that in microchips and stuff. I just don't see it happening.
You couldn't put feeling in one. I don't know how we'll get around that.
I think there'll never ever be a machine like us, like humans. But they're not going to be far away, but they're just not going to, otherwise we can quit now, can't we? You know?
The distinction many make between physical human bodies, which they believe could be replicated in androids or whatever, and our spiritual minds, which they believe can't, is the philosopher's old dualistic distinction between mind and body. And this represents one argument against strong artificial intelligence.
In order to see the inside of the brain, what we need to do is actually to separate the two hemispheres very carefully and pull them apart from one another, and that will enable us to have a look at the brain right from the inside. So as we begin to open it up, you can see the medial surfaces.
Most of us find it difficult to reconcile our picture of the physical matter which makes up the brain with a vivid consciousness which appears to result from its action.
Lobes of the brain, occipital, parietal, frontal, and then deep in the brain.
Surely we feel mind and body must be totally distinct things. What link can there be between that spongy grey matter of cell and tissue and the glorious, soaring insights of human consciousness? Happiness, excitement, sensation. We might believe that someday it will be possible to reproduce the machine that is our body. But how could we ever hope to reproduce the mysterious consciousness within it? Essentially, this is a mystical and religious view of consciousness, a profound phenomenon we ordinary humans will never be able to explain in physical or scientific terms. However much progress science makes in explaining things, there's always something beyond that explanation. Where does life come from? What came before the Big Bang? In this view, consciousness can only come from God and only be understood spiritually, not scientifically. And if we can't understand it scientifically, how can we ever hope to replicate it? This is a powerful argument, but it's not the reason why I reject the idea of strong artificial intelligence. I don't believe there is a straight choice between such a spiritual viewpoint and the materialism of the strong artificial intelligence position. I believe there's a third option. It is materialist in the sense that it argues for a physical and scientific explanation of consciousness, but equally it is opposed to strong artificial intelligence in that it argues that a materialist view of the mind does not inevitably mean that human consciousness is capable of being replicated in a computer. My option is less obvious than the other two, perhaps because it seems to cut across so much of late 20th century conditioning. It depends neither on yearning for spirituality nor on the sort of mechanistic approach to learning science which has become so familiar.
2 and 2 are 4, 4 and 4 are 8. That's all you have on your business like mine.
3 is 1. And the 1 you would place above the 3, which was the last figure that you used.
The way we learn mathematics, it is perhaps not surprising that many have come to believe that minds and computers work in the same way. The apparent link is a mathematical device for problem solving called an algorithm.
Is 18. You'd bring down the 6.
Much of elementary mathematics involves the following of step-by-step mechanical rules, such as in adding or multiplying numbers together. These operations are instances of what are called algorithms.
Leave you with 11. You then bring down the 125s, come to 175, and of course...
Examples of these systematic processes of calculation have been known since the times of the ancient Greeks. But it was not until the 1930s that the concept of a general algorithm was formulated.
1,747.
The man who formulated it launched a revolution that has transformed our world and created the arguments for strong artificial intelligence. Alan Turing was a mathematician of genius who helped break the Nazis' Enigma code at Bletchley Park during the Second World War and committed suicide in 1957 after being persecuted for his homosexuality. He left behind a legacy of work which laid the foundations of the computer age. In the 1930s, Turing had set out to provide a general definition of an algorithm. His approach was highly imaginative. He conceived of an idealized machine whose mechanical components, operating one after the other, corresponded to the step-by-step procedures of an algorithm. The Turing machine is essentially any object which carries out any purely step-by-step mechanical calculational procedure, and it is clear that in formulating his historic piece of mathematics, Turing was inspired by his vision of how the human mind worked. In his view, it was a Turing machine, working algorithmically step by step.
In this electronic age, computers are rapidly becoming man's best friend.
After the war, the idealized concept of the Turing machine inspired scientists to make it into a physical reality in the form of computers.
Problems at the speed of light and spew out the answers on punched cards, punched tape, or magnetic tape.
All modern computers derive from this. Serial computers, the kind most of us come across, which carry out computations one after the other.
C3?
Parallel computers, whose massive power comes from their ability to run a multitude of computations at the same time. All work algorithmically. While most computers are programmed so-called top-down, where their algorithms are fixed and dedicated to solving specific given tasks, some are programmed so-called bottom-up. Here their algorithms can modify themselves, but in an algorithmic way, so that the computer can, in a sense, learn from experience and can, for example, recognize patterns. Computers like this mimic the neural activity and architecture of the human brain, but essentially they are still just acting out algorithms. The algorithm is a universal concept which applies to everything which works mechanically. And whatever a Turing machine is made up of, silicon chips or old tin cans, it will always work in an algorithmic, computational way. Even the spongy grey matter of the brain could act as a Turing machine, and for the proponents of strong artificial intelligence, It not only could, it does. And that's all it does. The proponents of strong artificial intelligence argue that human intelligence acts according to algorithmic processes just like computers. When we start out, they say, we are like unprogrammed hardware. As experiences crowd in on us, we learn from them and process them, creating new algorithmic rules and programs as we go. According to this argument, we develop perceptual programs that allow us to read the physical world. We learn, for example, how to predict where an object that has disappeared will reappear.
Happy and sad. Which one's the sad?
We learn to recognize emotions in others and in ourselves. We learn rules that enable us to live as social animals, learn to make sense of the world. Of course, this process does not mean we all end up the same, like a run of mass-produced computers. We are individuals, each with our own personality. The strong AI position argues that this arises because each and every one of us is subjected to so many different and varied experiences that the outcome of the algorithmic process each brain goes through is unique. This algorithmic process is obviously highly complex and sophisticated, so not even the most committed proponent of strong artificial intelligence believes computers are yet anywhere near powerful enough to replicate human intelligence. For them, we may not be there yet. It is just a matter of time, development of sufficiently powerful computers and of the right algorithms before computers will be able to replicate human intelligence and then race beyond it. And because in their view thinking is computation, such computers will be conscious.
I think it's reasonable to view a nervous system as an information processing device built according to its own peculiar rules and restrictions. I see no reason to believe that there are any hidden processes which cannot be emulated in one way or another in other kinds of hardware. I don't think there's any magic in the nervous system other than its very clever organization and its very large complexity.
On the face of it, this might seem a persuasive argument. We have all experienced some kind of algorithmic thinking whenever we do a long division sum or follow the instructions as to how to use a calculator to do it, for example. Yet, while there is no doubt that some aspects of thinking are algorithmic and therefore replicable in computers, I shall argue that there are critical aspects of our consciousness which do not fit and cannot ever be fitted into this computational picture.
I like green because it makes me feel like Slimer. I like green because it makes me feel comfortable.
What is so special about human intelligence, consciousness, that it couldn't be replicated in a computer? As human beings, we experience the physical world through sensation. We can feel it. Take colors. Green, for example. We all know what the experience of green feels like.
It makes me feel slimy.
It makes you feel slimy. Ooh. Okay, what were you going to say, Jack? Fresh. Alfie, what does it make you feel?
It makes me feel nice and sleepy.
It makes you feel sleepy?
A computer-controlled robot could be programmed to respond to green, to pick out green materials, say, but that would not mean that the robot actually experiences green, as the children do. Instinctively, we feel a computer couldn't actually experience anything at all. For the proponents of strong artificial intelligence, this is an unimpressive argument. There is no difference, they say, between actually experiencing green and behaving exactly as though one is experiencing green. Well, that's a philosophical argument which could go on until the end of time. But there are kinds of human understanding which I believe more unarguably and scientifically demonstrate that they cannot be properly simulated by any computational activity whatever. Perhaps the most striking area of human understanding which cannot be totally simulated computationally is mathematics. This may seem odd, as mathematics might be thought to be a quintessentially algorithmic science. In many areas, like the carrying out of long division, it is, but in others, it's quite a different story.
Now, we've been looking at our times tables, and we have noticed, or rather you have noticed, a very interesting pattern.
In a very general and basic sense, although computers can follow rules, they can never understand those rules, which is what we can do.
If we've got three groups of two, we can represent that like this. Where I have now three groups of two. I put them together in an order, but we've got them there. 1, 2, 3, each group with 2 in. Yeah?
An example.
Okay.
How do we know that A times B will always equal B times A, where A and B are ordinary numbers? If we substitute actual numbers for A and B in each case, we can work it out.
They also give us the same answer here, 6.
It is also clear that the computer can work this out as well. But how do we know that this is true for any A and B whatsoever? We don't even have to know that 3 times 2 is 6 to see that 3 times 2 is the same as 2 times 3.
We know that we have 6 crosses. They could have been sweets, apples, whatever in your problem, but we have 6 of them in both sets. Are these two groups the same? Are they the same? Look at them. Are they the same? Kia?
Yes.
Yes.
They've got the same amount of cross inside, but they've been flipped over.
Rather than flip this over...
The children can see that it is, and we can understand along with them. To us, it's obvious.
Casper?
Rotated it.
We've rotated it. We've turned it or rotated it round to make this shape.
Now imagine the numbers are much larger. We don't have to count them all. But if we know there are A rows and B columns, then we know there will be A times B altogether. We can turn this round in our mind's eye and see that this must be the same as B rows and A columns. No matter how enormously big the numbers A and B, we know intuitively that A times B will always equal B times A. But a computer can only work it with actual examples. And since there are infinitely many actual numbers, no computer, no matter how powerful, would ever be able to finish the computation which would enable it to prove, merely by calculating, that A times B will always equal B times A. Of course, we could program the general rule into the computer, but it would not know independently of our telling it. It could not see, as we can, that the general rule must be true. Indeed, we could tell it that sometimes A times B is not equal to B times A, and the computer would have no way of telling that that was wrong. Now let's turn to something else in mathematics which computers can't cope with. The general problem of tiling the Euclidean plane. What, you may ask, is that? Imagine a plane stretching away into infinity. The task is to decide whether it can be covered all the way out to infinity without gaps or overlaps, using different kinds of geometric shapes, or tiles. If we have just one shape of tile, say this regular hexagon, the answer is obviously yes. And if the shape is this irregular pentagon, the answer again turns out to be yes. But if the shape is this regular pentagon, the answer now is an obvious no. We can also consider combinations of tile shapes. If we allow the use of this four-pointed star as well as the regular pentagon, then the answer is now yes. Though we do not ever literally cover the infinite plane, when we see enough of the pattern we can become confident that it will cover the plane. We can see this. Could a computer be programmed to answer correctly yes or no to the question of whether a particular tile shape or combination would cover the plane? Being algorithmic in operation, it would have to have a program, rules to follow. What might they be? It's noticeable with the examples so far that where the shapes successfully tiled the plane, in doing so they created repeating patterns. This insight could be programmed into the computer. It would know to answer yes if it detected that the pieces could be arranged in a way that produces repeating patterns. But does the answer yes occur only with shapes that create patterns that repeat? Look at this pair of shapes. The answer is yes. The shapes cover the plane, but they do not create a repeating pattern. The computer would be stumped. It could use its brute computing power to keep trying the shapes to see if they could fit and create a repeating pattern. Failing in this, the computer would wrongly answer that the shapes will not tile the plane. We could tell our computer that this particular kind of non-repeating arrangement also gives the answer yes. But that wouldn't solve the general tiling problem. To do that, we would have to keep supplying new insights like this forever. But the machine's meant to be computing this, not relying on our insights. No computer, no matter how powerful, could ever be able to finish a computation which would enable it to solve the general tiling problem for the entire infinite plane. The solution is literally non-computable. What might the strong artificial intelligence people say to all this? Well, they might say, fine, why don't we just build into the computer all the rules that can be perceived by human beings? Then it would do as well as we can, and do it a good deal faster and more accurately. And in any event, we humans work by such a set of rules. Rules that we have built up not only by the process of logic, but also through millennia of experience and natural selection. Well, they might say that, but a remarkable theorem formulated 60 years ago by a strange and brilliant logician proves that all the rules that can be perceived by human beings cannot be programmed into a computer. The Austrian mathematician Kurt Gödel was a genius, an eccentric, lonely man. He died at the age of 71 from malnutrition. He had stopped eating because he believed his doctors were trying to poison him. But while working in Vienna at the age of 25 in 1931, he transformed mathematics and logic with the profound and difficult work which will forever be associated with his name, the incompleteness theorem. Before this, mathematicians had been confident they were working inside a unified, complete system, and that any mathematical truth within that system could eventually be known. Gödel destroyed this belief. Gödel's enigmatic and challenging theorem revolutionized the basis of mathematics in ways that are still being explored. One thing it demonstrates is that whatever set of mathematical rules we choose to define the action of a computer, provided we believe those rules are right, then we must also believe, perceiving to be actually true, another rule that is completely inaccessible to the computer. In other words, every formal mathematical system, every system based on algorithms, must, if sound and perceived to be sound, be incomplete and perceived as incomplete. There will always be some propositions it will be unable to prove, but which we can perceive to be true. Algorithms are not the answer to everything. They do not encompass all human insights. There are some areas of mathematics, and hence of human understanding, that are not susceptible to algorithms, and so are inherently non-computable. But this is not the full extent of the importance of Gödel's theorem for my own arguments. Some wonderful insights that it contains provide critical support in other ways too. I believe Gödel's theorem provides wonderful insights into the nature of mathematical truth itself. If there's always another rule beyond any set of rules we've thought of at any given point, then the view that mathematics is invented by human intelligence must be wrong. I agree with Gödel that mathematics is not invented, but discovered. It has an existence independent of human intelligence. He tells us the world of mathematics is out there anyway, irrespective of whether we're here or not. This follows the ideas of the ancient Greek philosopher Plato, who argued for the existence of a perfect, timeless world, an ideal world. He believed the apparently real world we experience can only ever be an imperfect shadow of this Platonic perfection. We can continually uncover more of the truth of this ideal world through the use of intellect and insight, but we will never reach the end of the task. The Platonic vision isn't confined to mathematics. A Bach fugue has much in it of a deeply personal and emotional nature, but it is also continually striving for perfection, an ideal Platonic form. Many artists feel in their greatest works they are revealing eternal truths. Jorge Luis Borges, the Argentinian writer, said, "A famous poet is less of an inventor than a discoverer." But of all the forms of human intellectual endeavor, I believe it is mathematics, with its high degree of abstraction and conceptualization, that comes closest to embodying the Platonic ideal. Plato's ideal world contains mathematical truths accessible to us through our intellect. The real world consists of tangible objects accessible to us in the ordinary physical way through our senses. So the concepts of a circle or triangle, say, belong to the ideal Platonic world, while their physical embodiment in architecture, say, is a less perfect but real physical manifestation of that ideal. It may seem that there is little real connection between these two things, one abstract, one physical. But I believe these two worlds are inextricably bound together, and it is on that relationship that the next stage of my argument depends. I believe there is a profound harmony between the physical, actual world we live in and the Platonic ideal world. I believe this harmony is particularly significant in the case of the extraordinarily deep and integrated relationship that exists between mathematics, the abstract science of space, number and quantity, and physics, with its explanations of the workings of the physical universe. I recognize many may feel this is a somewhat bizarre proposition, that the extraordinarily complex workings of the physical world, everything from hurricanes to nuclear fission to terrifying fairground rides, can ultimately only be understood in terms of precise but abstract mathematics. Yet there is clear evidence for it. Perhaps the most striking demonstration is given by the most remarkable single scientific achievement of the 20th century. Einstein's general theory of relativity, formulated in 1915, was a Platonic theory, existing in an ideal world, beautiful in the magnificence of its mathematics, but unsupported by much in the way of observations of the physical world. Einstein arrived at it through extraordinary theoretical intuition and insight. It was only afterwards that observational evidence for the theory began to accumulate. During an eclipse in 1919, light was found to be displaced in accordance with the theory. Most strikingly, in 1964, astronomers at the Arecibo Observatory in Puerto Rico detected a double star system known as a binary pulsar, which emitted precise electromagnetic signals in a way that is now seen to be completely consistent with Einstein's theory. Largely on the basis of these observations, the general theory of relativity has now become the most accurate of all physical theories, accurate to 14 significant figures, 1 part in 100 million million. What mathematical theory supposed, physical observation has proved. The history of Einstein's general theory illustrates, I believe, the profound harmony between the worlds of mathematics and physics. What mathematics conceptualizes, physics demonstrates. I would expect to see a demonstration in the physical world of non-computability, which so far has been seen only in the abstract Platonic world of mathematics. I would expect to see that non-computability actually reflected in the physics underlying the activity of the world we live in, which includes the behavior of our brains. But is it? Physical theory currently operates on 2 levels of explanation. There is the level of classical physics, dealing with reasonably large-scale objects, things that we can actually perceive, like these fairground rides which harness known forces through familiar mechanics. Scientists like Newton, Maxwell and Einstein have given us remarkably accurate explanations of how the physical world we experience operates. They reveal the world as built up of small individual particles acting on each other through continuous fields of force permeating space. The gravitational force governs the motions of planets and physical bodies, while the electromagnetic force controls the behavior of charged particles and explains the nature of light and radio waves. There are precise equations which describe how these fields and particles change over time, and these equations can be solved to any desired degree of precision by algorithmic computation. No non-computability here. So what of the other level of explanation? Physicists in the early years of this century developed the theory of quantum mechanics to provide an explanation for the behavior of matter at the molecular, atomic, and subatomic level, well below that which we can directly perceive. It describes nature by what is called the quantum state, where particles are considered as spread-out, wave-like structures, inextricably entangled with one another. It explains a wide range of phenomena from lasers to the colors and physical nature of substances. The quantum state evolves according to a very precise equation. Here, too, the equation can be accurately described by algorithmic methods. So the quantum level is also computable. If both the existing levels of physical explanation of the world are computable, then it might appear that there must be a serious flaw in the argument. After all, my claims resting on non-computability in mathematics, and also on my belief in the profound harmony between mathematics and physics, suggest that there will be elements of non-computability in the physical explanation of the world. And it might appear that this is not the case. as both the existing levels of physical explanation, the classical and the quantum, are completely computable. But there isn't really a contradiction here. That's because these two levels of explanation, good as they are, do not provide a complete framework for the explanation of the physical world. It is in the gap between them that a new theory of physics is needed, and where I believe the non-computability I predict for the physical world will be found. The development of quantum theory at the turn of the century by scientists like Bohr, Heisenberg, Schrödinger and Dirac was a remarkable scientific achievement. But it raised as many questions as it answered. Quantum theory is very difficult to grasp because it posits a view of physical behavior which seems to run directly counter to common sense. At the classical level, although there is the possibility of many things happening, only one thing actually happens. But quantum theory argues that all the things that might happen actually happen together, existing in some strange kind of superposition, something common sense and common experience tells us is impossible.
One of the originators of quantum theory, the famous physicist Schrödinger, was particularly troubled by this discrepancy. He invented a thought experiment, much imitated, to illustrate the profound philosophical problems that arise as a result. Imagine my version of it. A ceramic cat is placed close to a large hammer capable of smashing it to pieces. The hammer is released by a mechanism triggered by a quantum event. Say the activating of a photoelectric cell by a photon emitted by some light source. In between is a half-silvered mirror. The photon may be reflected off this, in which case the cat survives. But the photon has an equal chance of passing through the mirror, activating the mechanism, and smashing the cat. Quantum theory tells us the photon is both transmitted through and reflected off the mirror, leaving the cat both smashed and not smashed at the same time. But this is absurd, for all our experience tells us that the cat must be in one state or the other. Quantum theory copes with this discrepancy by asserting that when a quantum event is magnified in this way so that its effects become large, like smashing or not smashing a cat, then something happens on this journey from the microscopic to the macroscopic. That something is often referred to as the collapse of the wave function, when the quantum world of multiple possibilities becomes the classical world of actual outcomes.
Schrödinger invented this thought experiment to demonstrate a gap between the explanations of quantum theory, operating at atomic and subatomic levels, and classical theory, which explains more massive phenomena. No one knows exactly how or why the wave function collapses from the quantum world of multiple possibilities to the classical world of actual outcomes. So it seems to me that there is clearly a need for a new physical theory to bridge the two existing levels of explanation. And it is in this bridge that I believe we will find the elements of non-computability my argument predicts.
We are a long way off from any formulation of such a theory, but there is already evidence that suggests that it must operate in the workings of the brain. The conventional picture of brain action is one of classical level physics, with the brain cells known as neurons carrying and switching electric signals through an elaborate network. This looks very like the classical model of a computer, with the neurons acting as the computer's transistors and wires. But this does not provide the support it might appear to for the strong AI position. For this is not all there is to the brain. Deep below the level of neurons lies a substructure known as the cytoskeleton, with filaments of tube-like fibers known as microtubules, acting in complicated ways, controlling the connections between one neuron and the next. The cytoskeleton operates at a level where quantum laws apply, but through the microtubules it also influences the classical level world of the network of neurons. And it is at this transition level between quantum and classical physics where a new theory is needed, not just for the operation of the brain, but for much else as well. A theory where there will be found the elements of non-computability I predict. I believe this theory will surely emerge one day.
In science, explanation is usually eventually followed the perceived need for it. And when it does, I believe we shall then have the physical support for my mathematical argument that non-computability is an inherent feature of our world and our consciousness that perceives it, and that computers will thus never be able to replicate such human consciousness.
What's one way of saying this then, Lawrence? 2 lots of 3.
It may be one day computers will appear to learn to think and exhibit intelligent actions, but they will never possess consciousness. Whatever the mind is, however it gives rise to human intelligence and consciousness, it must be something that is inextricably intertwined with the very laws that govern the workings of our actual universe, and with the deep and intimate way these laws relate to the Platonic mathematical realm. The place of mind in the universe is neither a gift from God nor a cosmic accident. It is bound up with the very foundations of the mathematical laws governing physical behavior. And because some of the most fundamental elements of those laws are non-computable, computers will never be able to do more than simulate the computable aspects of human intelligence. Computers are immensely powerful tools that will achieve even greater powers in the future. Incredibly powerful computers, yes. But as for replicating human intelligence, they are the delusion of the emperor's new mind.